Dude, I'm so glad we're done with that catapult. That thing was a pain.
Yeah, bro, I know, right? Like, thank God we're done with that catapult. Oh,
It was at this moment that he knew. He fucked up.
shit, wait. Dude, we forgot to make the video.
Dude, you're so right, man. Dude, what time is it?
What time is it?
Dude, it's 11 p.m. It's due in an hour.
Oh, shh.
Dude, we need to go. Yeah, we need to go.
A few inches later.
Okay.
Okay, wait, so, what do we even have to do for the video?
Dude, I don't know. I didn't even turn the back of the page.
Wait, I heard Miss Trioni says that we have to, like, answer these questions about our catapult.
We do?
Wait. Oh, yeah, this paper. So, wait, what is the first question anyways?
The first question is, describe how your apparatus applies a net force on the ping pong ball in order to accelerate from rest. Use your apparatus as a visual aid while you describe this.
Bro, that's hella easy. I could do that right now.
Okay.
The apparatus applies a force on the ping pong ball perpendicular to the arm of the catapult. And by pulling down on the arm of the catapult, we are storing the potential energy of the catapult in the tension in the arm. Also, a force is being applied off the center of mass on the arm of the catapult. Therefore, there is no torque. Torque is the force that causes rotational motion. When launching, the arm makes an arc with radius equal to the arm length. Therefore, the potential energy is transferred into rotational kinetic energy. The moment of inertia, also known as the angular mass or rotational inertia, expresses a body's tendency to resist angular acceleration and determines the torque needed for desired angular acceleration about a rotational axis, similar to how mass determines the force needed for desired acceleration. The moment of inertia, as the arm is a rod and it is rotating on its end. Due to the law of conservation of energy, all the potential energy is transferred into rotational kinetic energy. The angular velocity is transferred into linear velocity when the arm comes to a halt, and the ping pong ball continues in the direction of its linear velocity trajectory. Essentially, the apparatus applies a force on the ping pong ball perpendicular to the arm of the catapult.
Okay, yeah, that was a good explanation, but we also have to make a 2D visual of a zoomed picture of your apparatus launching the ping pong ball and draw it in the vector of showing the net force being applied to the ping pong ball as well.
Shit, dude, are you serious?
Yeah.
Okay, wait, let's just quickly do that.
Dude.
This photo shows the net force acting on the ping pong ball from the apparatus. So, basically, the direction of the force is perpendicular to the length of the arm, and the magnitude of the net force is greater than 0 because the apparatus applies an unbalanced force to the ping pong ball. This unbalanced force is what causes the ping pong ball to accelerate from rest. A diagram shows the direction and an estimated magnitude of the net force. Also, this second diagram shows all the different forces acting on the ping pong ball. The force of gravity acts straight downwards on the ball, while the normal force is perpendicular to the arm of the catapult. Similarly, the force applied by the apparatus is applied perpendicular to the arm of the catapult. The length of the vector sum of the normal force and the catapult force is longer than the length of the gravitational force in the diagram, because in order for the ping pong ball to be accelerated, the force acting in that direction must be greater than the force of gravity. And therefore there is an unbalanced force in this situation and the ping pong ball is not in equilibrium.
Okay.
Alright, so what's next?
Alright, question 2 is describe all the forces on the ping pong ball at the moment it leaves your apparatus. This is the moment where it is no longer touching any part of your apparatus. Use your apparatus as a visual aid while you describe.
Oh wow, dude, that's actually hella easy. I could do that too.
Dude, okay.
Yeah, oh my god. Wait, let's get do. This diagram represents the forces acting on the ping pong ball the moment it leaves the apparatus. So basically, the moment the ping pong ball leaves the catapult, it enters free fall, and the projectile, in this case the ping pong ball, will travel with a parabolic trajectory. If we neglect air resistance or friction, the only force acting on the ping pong ball the moment it leaves and is no longer touching the apparatus is the force of gravity, accelerating the ball downwards at a rate of 9.8 meters per second squared. This means that if we define straight up as the positive y direction, then the ping pong ball's velocity is decreasing by approximately 9.8 meters per second every single second.
6.5 hours later.
Oh shit.
Okay. Alright. Question 3 says.
Wait, what time is it? Wait, let's check the time, please. Oh shit, it's 11:20. Oh my god, we only have 40 minutes. Come on,
Okay.
let's go.
Question 3 says describe the distance your ping pong ball travels from the time it is sitting in the release mechanism to when it first hits the ground.
Bro, this is hella easy. I could do that too. Come on, dude, let's go do that.
Yeah.
Okay, so the ping pong ball travels a distance over a parabolic trajectory, and in order to estimate the distance that the ball travels, you need to find the displacement of the ball from its starting position to its max height position, then calculate the displacement of the ball from its max height position to its end position and add them up. So in order to find the displacement from the starting point to the point of max height, you calculate the change in y position and change in x position, then use the Pythagorean theorem to find the diagonal length. Then you would do the same for the displacement from the point of max height to the end point. And here is a visual to show you a possible way to estimate the distance traveled by the ping pong ball, although it is not the most accurate way. Okay, so here is a visual to show you how to calculate the distance traveled by the ping pong ball over its trajectory, although it's not the most accurate way. Okay, come on, hurry.
Okay, yeah.
What's
Part
the
B
next question?
says in your video show a group member measuring or calculating the distance. If you need to estimate the distance, explain why you need to estimate and how you estimate.
Okay, dude, I can do that too. Come on.
Alright, let's go do it.
Okay, so to calculate the distance that the ping pong ball travels, so first you would find the sum of the lengths of C1 plus C2 as shown by the diagram, and C1 plus C2 would be the estimated distance. So by the Pythagorean theorem, C1 equals the square root of A1 squared plus B1 squared, and C2 equals the square root of A2 squared plus B2 squared. So in this trial, A1 equaled 1.9 and A2 also equaled 1.85 after we measured. And after measuring the max height that the ball reached, we found that B1 equals 0.8 and B2 equals 0.69. And by the way, we're doing all our calculations in meters, kilograms, and yeah. So by using the Pythagorean theorem, C squared equaled the square root of A squared plus B squared. And we calculated that C1 equals 2.06 meters and C2 equals 1.98 meters, and the total distance traveled in this trial was the sum of C1 and C2, which was 4.04 meters with sig figs. Oh my god, okay, one more.
Alright, so question 3C says measure, calculate, estimate for 5 trials. In your video, show a data table of these trials and state the average distance in meters.
Bro, this is easy money. Come
Dude,
on, let's go do that. From this table, we can see that the ping pong ball traveled an average of 4.28 meters for its distance over 5 trials. Dude, oh my god, we're halfway done.
I know.
Wait, oh shit, what time is it? Wait, check your phone.
Dude, it's 11:30.
Okay, we gotta hurry up. Okay,
so
what's the next question?
Question 4 says describe the displacement of your ping pong ball from the time it is sitting in the release mechanism to when it first hits the ground or table.
Oh shit. Okay, wait, I think I could do that. Wait, let's get straight to it. Come on. Oh yeah, so the displacement traveled by the ping pong ball is the length of the direct line from the start point to the end point of the projectile path.
Okay. Alright, so For B of question 4, it says, in your video, show a group member measuring or calculating the displacement. If you need to estimate this displacement, explain why you need to estimate and how you estimate it.
Bro, that's like the same as the question before. Come on, let's do it.
Let's go.
Okay, so to calculate the displacement, first we measured the x distance away the ping pong ball landed from its starting point. Then we calculated the difference between the heights of the start point and the end point, and by using the Pythagorean theorem we calculated the displacement. So in this trial, the change in x position was 0.8 and the change in y position was 2.9. So substituting these values into the Pythagorean theorem, c squared equals the square root of a squared plus b squared, we calculated that the displacement in this trial was 3.01 meters after sig figs.
Ooh. Oh, okay.
Okay, last one for 4.
Okay, so it says measure, calculate, estimate for 5 trials in your video. Show a data table of these trials and state the average displacement in meters. Okay.
Okay, let's do it.
Yeah, we got
let's
that.
do it. From this table, we can see that the ping pong ball traveled an average displacement of 3.024 meters over its 5 different trials. Okay, wait, let's check the time real quick.
Okay.
Oh my god.
Dude, it's 11:40.
Oh shit.
Okay,
we're
dude.
late.
Yeah,
Yeah,
okay.
shit.
Okay, so question 5 says, explain whether or not the ping pong ball moves with constant velocity. If it does not, explain why not. If it does, explain when. If it moves with constant velocity at multiple times, locations, explain all of them.
Oh dude, I actually don't know how to do this one.
Dude, no worries, dude. I actually was paying attention to Miss Shioni's class,
Really?
and we learned this. Don't worry, we
Oh,
got this.
thank
Let's
God.
go.
Yeah, let's go.
I actually was paying attention to Miss Shioni's class,
Really?
and we learned this. Don't worry, we
Oh,
got this.
thank
Let's
God.
go.
Yeah, let's go.
First, let's assume that the direction of positive motion is directly upwards. The ping pong ball moves with a constant velocity in the x direction, which is perpendicular to the ground, but it accelerates in the y direction. Therefore, it doesn't move with constant velocity. Acceleration, a vector quantity, is either a change in speed or a change in direction. To calculate acceleration, you take the change in velocity and divide it by time. The ping pong ball is accelerated in the y direction because the force of gravity accelerates it in downward at a rate of about 9.81 meters per second squared. The force of gravity both changes the velocity of the ping pong ball and changes the direction that the ping pong ball is moving, so therefore the ping pong ball doesn't move with constant velocity. The moment the ping pong ball leaves the catapult, it enters free fall. In fact, the projectile, in this case a ping pong ball, would travel with a parabolic trajectory going back. The presence of gravity does not affect the horizontal motion of the ping pong ball. This is because the force of gravity is a vertical force and does not affect horizontal motion. Forces can be broken down into x components and y components, which are perpendicular to each other, and motions that are perpendicular are independent to each other. Alright, to give a visual example, we can draw it out using vectors. Let's just assume that at t seconds, a downward force of gravity is acting on the ping pong ball while it's in midair. Let's assume that the ping pong ball has a velocity in the direction parallel to the surface of the ground by adding the vectors using the head to tail methods. The resultant vector, which represents the ball's new velocity, is in a different direction than the original velocity vector. This change in direction causes the ping pong ball to not move with constant velocity.
Oh shit. Okay, wait, what time is it? What time
Dude,
we
it's
have left?
11:50.
Oh no, we have to finish. Come on, we gotta hurry.
Okay, so question 6 says, explain whether or not the ping pong ball moves with uniform acceleration. If it does not, explain why not. If it does, explain when. If it moves with a uniform acceleration at multiple times, locations, explain all of them.
Oh shit, dude, I don't know how to do
Don't worry,
that.
I got this.
Oh really?
Let's go.
Oh yeah, let's go then.
Once released from the catapult, the ping pong ball is only affected by gravity, so the ping pong ball does not move with uniform acceleration the entire way. The ping pong ball is constantly being accelerated downward at a downward rate of 9.8 meters per second squared. Vertical motion is under Newton's second law, therefore the ping pong ball is at a constant downwards acceleration. However, while the catapult swings the ball and the ball is still in contact with the arm of the catapult, the direction of acceleration is constantly changing, so the ping pong ball does not move with uniform acceleration while being launched on top of the arm of the catapult.
Oh shit, okay, we're done.
Dude.
Dude, we're finally done. Wait.
Alright dude, it's 11:52.
Shit, but we didn't edit the video yet.
I know, we got 8 minutes. Let's get
Oh my
this
god,
video
okay, yeah, let's go.
Oh my god, okay, we need to go now.
Oh my god, I'm so tired. What time is it? Oh shit, it's 11:55. Oh my god, I have 5 minutes. Oh my god. Okay, come on. What time is it? Oh no, it's 11:57. Oh my god, I got 2 minutes to edit this video. Come on, come on, come on. Okay.
Nope.